Never mistake motion for action, in the words of the Nobel laureate Ernest Hemingway. Paraphrased for relevance to science and motion, it could be read to mean how there is much more to motion than the visible, motion or change characteristics, such as time and distance. The real action away from time and distance may well be more revealing. Motion is the simplest study of nature of change. Motion may be the simplest example of discernible primary, that is physically measured, and derived, that is mathematically measured, physically immeasurable, quantities or features of change. The derived quantities are at least as important as the primary quantities. The exploration of the motion is aimed at getting an understanding of the derived quantities. Changing positions is being in motion. It is the most visible effect of motion. The first attribute of anything in motion is a starting and a finishing position. The two may overlap, as in a circular motion. The second feature of being in motion is a path, that is the series of positions, from the starting to the finishing positions. There has to be a path to reach the finishing position. However, positions are not anchor enough to uniquely specify a motion. The first picture shows the first reason for it. Between start and finish positions of a motion, there could well be infinite possible paths for the motion. The second picture shows the second reason. We need infinite positions between the starting and finishing positions to fix a path. It is obviously not possible, let alone convenient, to list infinite positions between the two terminal positions to trace a path of motion. We need to move away from motion being defined using positions, except for the starting and the finishing positions. Positions are not practical means of showing path of motions. Interestingly, distance is a substitute for positions of the path of motion. Using just a number for the paths between 2 points instead of stating the infinite positions is practically the simplest solution. Distance, just a number, shows a near unique path of motion between 2 points. Yes, for a given amount of distance, there would be infinite paths between 2 points. But imagine how many practically advisable paths may exist going from point A to point B in your city. Indeed, for realistic motion possibilities, there can only be a few alternate paths of the same distance. And, practically speaking, just one of the same distance in a real-world scenario, such as the popular path, best timed path, etc. Distance is the practical choice for quantifying motion. Distance is indeed a practical and simple primary descriptor of motion. It is the length of the chosen path of a motion. The graph shows a straight line motion. It simply shows the distances traveled over time. The key idea is distance can be graphed, pictured. Let us evaluate distance as a measure of describing all about a motion. Also because distance is easily measured quantity in motion. The picture shows two cars in motion. One of them traveled a distance of 300 kilometers in a day, and the other a distance of 600 kilometers on the same day. What inferences may be made for certain about the motion of the cars? Only the distance, or the length of the path of motion, is given. The following are the inferences regarding the motion of two cars. First, the first car is closer to home, or the starting point. Second, the second car is farther away from home, or the starting point. Third, the second car traveled a longer, actually double, the distance compared to the first car. We know little else, such as time to move 300 km or 600 km. To know more about the motion of the two cars, let time data be also added to the distance data on the motion. Time is the other natural feature of motion. A motion happens over a period of time. The change of positions in motion happens within a non-zero time lapse. That is, it takes time, howsoever small, for a movement from position A to position B. Let us evaluate what more do we know about a motion if we know the distance traveled and the time taken for it. Consider. One of the cars traveled a distance of 300 kilometers in 2 hours, and the other covered a distance of 600 kilometers in 6 hours. The following are the inferences regarding the motion of two cars with known time and distance. The first car traveled 300 kilometers. The first car took 2 hours. The second car traveled 600 kilometers. The second car took 6 hours. The second car took thrice the time to finishing point compared to first car. Once again, the use of time data is not bring any additional insights into the motion of the car. For example, we do not know why the second car took thrice the time to travel double the distance of the first car. We do not know if the first car traveled 150 kilometers in each hour. We do not know if the second car traveled for 100 kilometers in each hour, and more such aspects of motion are unknown. An important lesson is that the quality of insights into motion do not improve, even when both the directly or physically measurable quantities of any motion, time and distance, are known. There is little more than what is given, total time, total distance. We need to look beyond the values of time and distance to know more about motion. And this is expected, because time and distance are mostly static, non-dynamic reflection of motion. The two are directly measurable. And that implies time and distance measurement kind of necessitate at least a momentary stoppage of motion to measure the time and distance measures up to that point. Indeed, time and distance by themselves do not bring out the continuous change that is motion. Time and distance are just gross measures of motion as change. Expectedly, we need new ways to describe motion that captures its dynamic part, the changes in the nature of motion from instant to instant. Measures that show the continuous change part of motion. Recall, the dynamic part of any change is the rate of its change, how much fast or slow, and whether further increasing or decreasing at an instant. And this is the key to best understand all continuous change. Motion is also better understood when we know its speed, the pace of change in how it is covering distance. And that means the level of pace and whether further increasing or decreasing. Rate is not directly measurable. Speed of motion has to be derived, calculated from the two known measurable quantities, distance and time. Next, we see what is rate, mathematically speaking. Mathematically, rate is a relationship between two quantities. Rate is a special form of ratio of two quantities. We use rate very extensively in everyday living and work. For example, price of something per liter, heart rate, inflation rate of the economy, evaporation rate of the weather on a day in millimeter per hour or inch per day. In mathematics, ratio is the only way we show the direct quantitative relationship of two things. For example, the ratio 6:3 may show the relationship of car parking spaces to number of houses in an apartment block, that there are 6 car parks for every 3 houses. Rate is a special form of ratio because the consequent number, the second number of the ratio, is always one unit of quantity of something. Thus, for the house and car park ratio, the rate form will be 2:1, 2 car park spaces for every 1 house. Thus, rate may be seen as the way we express how two things behave in sync in quantity terms. Rate simplifies the use of ratios, makes the significance, meaning, and application of ratios just a matter of simple scale up or down quantitatively. We are now ready to get to what is rate of change, the key measure of continuous change. As the name suggests, rate of change is the rate of changing quantities. That is, the ratio of how much something has changed for one unit of change in the other quantity. For example, the change in distance covered when time changed from 15th to the 16th second. Rate of change is change in something for every 1 unit change in another. The rate of change is about relationship of simultaneous quantitative change in two things. The rate relationship between distance and time gives us a very important, useful, and new view of motion, beyond the time and distance data of motion. This rate relationship tells us the distance traveled in any one unit of time. For example, it could be 20 meters per second, 30 kilometers per hour, or 45 millimeters of rain per hour. We all know this as speed of motion. Rate is in general the mathematics of speed of all kinds, such as annual interest rate, which is interest per 100 per year. Rate has to be computed, that is mathematically derived, from distance and time which are directly measured. Back to the example of the two cars. Let us now explore what we know more about the motion of the two cars using the computation of the rate of motion or the speed of motion, computing how much distance is covered in 1 hour by both the cars. For the first car, the speed is 150 km per hour. The car covers a distance of 150 km in each 1 hour of the 2 hours. Because we only know the total time and distance, we can only compute the speed of the total motion. But how real is that the first car travels at the same speed over 2 hours? And for the second car, the speed is 100 km every hour for 6 hours. And how real is the same speed for 6 hours? And there is more when we compare the two speeds. For example, does this mean that the first car always drove faster than the second car? And how can we be sure? In fact, this speed computation based on total time and distance is too gross, general, and far from telling us the complete picture. Recall, it does sound unreal that the cars ran at the rate of 150 km per hour for 2 hours and 100 km per hour for 6 hours. It is also possible that the cars never ran at exactly 150 km per hour and 100 km per hour. The rates are gross, not specific to any instant of the motion. In fact, this rate has a name, average speed. And it is useful, but only in a broad, sweeping way. Averaged quantities have the following relevant characteristics, expressed through the example of average speed. First, the computed average speed may not be same as the actual speed at even one instant in the motion. Second, the actual speed at any instant may well vary from 0 to multiples of the average speed. Third, the actual speed at various instants have to be found for the instance. Briefly, it is the mean or the leveled speed. That is, it is the one speed that is analytically derived from mathematical formula. Any quantity, including rate when averaged, ride over variations, and deny the reality of changing quantities. Unsurprisingly, average speed can throw surprises. For instance, it hides real possibilities of mishaps. Referring to the two cars examples, it is very much possible that the slower average speed car at 100 km per hour has higher chances of skidding at the sharp turns on the way as compared to the faster average speed car at 150 km per hour, because the speed at those sharp turns could be far higher than the average of 100. The slower average speed car could also be prone to excessive damage in case of an accident if the speed at several instants go up real high. To the point, it is the instantaneous speed that matters more than the average speed. To be true, we need to find the mathematics to compute the instantaneous speed of the two cars, to know more details about their motion. It may be reiterated that speed, a rate of change, is not directly measurable and hence has to be derived from analytical means using mathematics. Thus, instantaneous rate or speed demands newer mathematical capabilities. It is what calculus is about. Calculus helps us calculate the actual rate of motion at any instant or set of instants. Hopefully, the distinction and character of average and instantaneous are well articulated. We can summarize the distinction between the two in 4 statements. Both reflect the rate of change of distance. Thus, both have the same mathematical derivation: distance traveled by time of that travel. In other words, final position minus initial position. By time of that travel, time of travel in instantaneous speed computations is very small. For simplicity, we can say that the instant for the average speed is much longer. Finally, we are ready to step into the exploration of the new mathematics that is focused on finding the instantaneous values of changing quantities. That is, finding the instantaneous values of rate of change. The rate of change formula, when used for computing any instantaneous values, such as instantaneous speed, reduces the unit of time to be near 0, that is instant time. We are now at the threshold of new mathematics of finding and working with rate of change. It is what we call calculus. And from what we know about instantaneous rate of change, what may be the new mathematical innovations brought about by calculus? Any guesses? 3 challenges could be identified in finding the instantaneous rate that calculus addressed. The contours of measuring rate of change suffered from 3 challenges for all of history till the invention of calculus by Isaac Newton and Gottfried Wilhelm Leibniz in the 17th century. The 3 major challenges in computing the instantaneous rate of change, exemplified by the rate of change of motion, are: first, how to accurately measure the rate of change in an instant of time. In the case of motion, it is measuring speed at any definite time, at a near zero duration of time. Second, how to quantify or numericalize that instant of time, that is, what is that non-zero duration of time that is almost as good as zero for the thing that is changing. Third, how to be sure that the chosen quantity of the non-zero instant is relevantly small enough to ensure to get us an unchanging rate of change for that instant. It should not be that the rate of change varies in the chosen quantity of instant. Let us briefly touch upon why ensuring the quantity of the instant, the near zero time for instance, is critically important in calculus. It should not be that the rate of change varies in the chosen quantity of instant. 2 situations are easily visualizable wherein the rate of change, that is speed, may change in the chosen quantity of instant. When the instant is bigger than necessary and when the instant has a situation of sharp change in the rate of change. These 3 challenges were inventively addressed by calculus, and that revolutionized our ability to measure change. The need for these innovations is obvious from the near zero unit of time. Last but not the least, it must be just placed on record that time is not the only dimension for finding the rate of change. That is, the measurement of change of any quantity could well be with respect to quantities other than time. For example, we can consider a change in the volume of a spherical balloon with respect to its radius or surface area. We will explore more of this in derivatives or differentiation. Thank you. With us, you will master all the mathematics you need. Be good to you, not just others.